Thank you very much to you for announcing the speaker. So thank you for the organizer, So my talk would be an overview about p-adic differential equation on Berkovich curve. I assume that the audience here is divided in two groups. One group come from Berkovich geometry, the other comes from differential equation or p-adic representation. So I decided to give a large introduction and establish some notation that for many of you are quite clear. So it will be an introductory lecture on this subject. So I will, in the first part, I will give a large introduction. In the second, I establish some notation about Berkovich curves. And in the third one, I will speak about some recent results that we have obtained since 2012, more or less. Okay, let's start with the introduction. I'd like to list some major historical landmarks, first of all. So this theory has a date of birth. The date of birth is the date where Dwork proved the rationality of the zeta function of an algebraic variety of positive characteristic. He proved this with the use of a certain differential equation, and after this he defined a sort of the Rham cohomology that was called Dwork cohomology at that moment. So we assist then to several works of Dwork, Roba, and many others. They was mainly dealing with differential equations on the affine line and with the modern language of Berkovich. Most part of them was results in a neighborhood of a Berkovich point or over the Roba ring. In 2000, we have Kristol and Mevcut results together with the contribution of many other people. They are studying mainly differential equations over the Roba ring and obtain applications over rigid curves. And there is also the link with p-adic representation at this moment. So 10 years later, we assist recently then to a generalization of a globalization of the world theory of Berkovich curves. The actors here are Baldassarri, Kedlaya, Poineau, and myself. Okay, so let me say some word so we can use the several kind of languages to describe the space that is underlying to the differential equation. So, for instance, Tate, Renaud, Berkovich, Huber, Meredith. But let me mention the language of rigid cohomology, which is particularly important in my opinion. So the major aim of this theory is to find a good category of coefficients over any variety in positive characteristic. And these coefficients are essentially some differential equations defined over the generic fiber of a certain model of the variety. The fiber has a structure in a natural way of Berkovich space. So let me say that these equations usually come with together with some operator and some restrictions. So a question may be asked, why do we really need a p-adic cohomology theory? Because we already have the L-adic theory that works very well. So the reason is that p-adic differential equations are more explicit in some sense and allow sometimes direct computations. So the point of view of this talk is somehow orthogonal to that of rigid cohomology, because we give to ourselves directly a Berkovich curve together with a differential equation on it with no restrictions. So an arbitrary differential equation on it. And at this level of generality, few results are known, especially for the finiteness of the Rham cohomology. Even in the simpler case of a disk or an annulus, essentially there are no criterion describing no criterion describing the finiteness of the cohomology. Results in this direction have been found by Dwork, Robach, Kristol, Mepkut, and as I have mentioned, they are essentially a local nature in the sense of Berkovich. So the starting point, the central problem here is the following. So if we have a differential equation over an open disk, the equation is possibly non-trivial. In another way of thinking, the solution of this equation are not converging on the whole disk. So, for instance, if you have the same kind of problem over the field of complex numbers, so for instance, if you consider C itself, the affine line, and you remove some points, so your equation has some singularity over the affine line, the complex affine line. And if you have a differential equation over this Zariski open of the affine line, then any formal solution of the equation converge until the first singularity of the equation. But here we have several examples, even in easy cases. Consider these equations. This equation, the easiest one, the solution is the exponential, but the exponential doesn't converge on the whole affine line. So the reason why the exponential stopped converging is a sort of mystery. Okay, because there is no singularity. So there is no physical obstruction to the convergence. So I'm not going to answer to this question, but I'm trying to, studying the behavior of the radii of convergence of the p-adic differential equations, because it is one of the major invariants of this theory. So let me continue my introduction by recalling some of the major ideas of the pioneer work of Dwork and Robach. For example, the overconvergence, or the introduction of a Frobenius structure, solvability, and the composition by the radii, the relation between the radii and the cohomology. So this idea influenced most part of the literature. So I wanted to recall that most part of the idea that you see here come exactly directly from them, especially the relation between the radii and the cohomology. This was established by Robach itself. After their work, several other authors tried to generalize their results in several directions, but the direction that are interesting in this talk will be factorization and decomposition theorems by the radii. I will be more specific in the next slides. And application to the finite dimensionality of the Rham cohomology and index theorems. So recently, in 2010, we assist at some important result of global nature. First of all, let me mention the book of Kadlaya of 2010. So it contains important improvements of classical results. I think this is a kind of reductive description of the book because it contains several important things. One of them is new decomposition results of global nature over disks and annuli. We have the result of Baldassari following a common work with Di Vizio, 2010, more or less simultaneously, and about the continuity of the first radius of convergence. So I will be more specific in some slide, but let me say here that so to each point of the curve you can associate the radius of the greater disk where the equation becomes trivial somehow, and you get in this way a function on the curve, and the theorem asks that the function is continuous. So where all the solutions converge, okay, the disk where all the solutions converge. So after this, in a sequence of works, most of them in collaboration with Jérôme Poineau, we have generalized the continuity by proving actually a finiteness property. This finiteness property means, roughly speaking, that the radii of convergence are functions that are controlled by a finite number of quantities. More precisely, this function factorize through a finite graph inside the curve. So we have used these new results to establish some decomposition theorem of global nature, and we have proved the finiteness of the Rham cohomology under certain mild conditions.
You mean for the curve?
Over curve, everything is over curves, yes. And very recently I also obtained a link with the Riemann-Hurwitz formula, but I don't think I will speak about this in this talk. I mentioned a paper of Kedlaya, more or less at the same time, where he generalized the p-adic local monodromy theorem. He also reproved the result about the finiteness of the radii. Finiteness. So he showed also that the controlling graph, so the graph where the radii factorize, contain no points of type 4. And then he also improved the theory of exponents of Kristol and Mepkud, and I think his talk is going to be on this last point. Okay, very recently, Poineau and Berkovich described the behavior of the radii by push forward and provide a relation with the ramification theory between curves. Okay, let me start now then with the notation on Berkovich curves. I assume from now on that our field is of characteristic 0, and then that is algebraically closed. This is a simplification for this talk. So a curve is called the rig smooth or quasi-smooth if the omega 1 is locally free OX model of rank 1. The thing that you have to keep in mind is that we allow boundary on the curves. For example, a closed disk has a boundary and is a rig smooth curve. Well, let me show you some picture that some of you know very well, maybe all of you. This is the picture of an open disk. It is a tree, topologically speaking, and you may have bifurcation points, some other points that are not. It is an infinite tree usually. And the last point here is missing. So this is a closed disk. So these circles here are open disks, resumed in this way. There is one point where every disks meet, and this is the boundary of the closed disk. Notice that the union of all the open disks is not the whole closed disk. There is one point missing. So if you want a covering, you have also to cover this point by some finite neighborhood. Okay, the space is connected and we have one point. What is an annulus then? An annulus, topologically speaking, is similar to this picture. We have a skeleton, a red line, and some disks that are branched on this skeleton. Okay, so if you give me a rational point, I can consider the largest disk, the largest open disk containing the point and contained in the annulus. It is one of those points. The relative boundary of this open disk will be a point of this skeleton. Actually, the set, the red line here can be described as the set of points that have no neighborhood isomorphic to a disk. What happens if I remove one point from my disk? I remove this point, and what remains here is an annulus together with a union of disks. This is actually a general fact, so I'm going to speak about the structure, or the general structure of the quasi-smooth curves, but I need a slide about the type of the points. So there are 4 types of points. Type 1 points are rational points, k-rational points. Type 2 points, so they live at the end of the graph. Type 2 points are bifurcation points, topologically speaking. All of this is quite informal, of course. And type 3 points are not bifurcation. They only have 2 directions out of them, and they are in the middle of the graph. Type 4 points are endpoint of the graph, but they are not of type 1. They are in the middle of the graph. So if our base field is quite large, spherically complete, for instance, then there are no type 4 points. So let me speak about the structure of the curve, so semi-stable reduction theorem. In this form, I think the theorem is due to Berkovich and Ducrot. So let me consider a quasi-smooth curve. The theorem says that there exists a locally finite subset formed by point of type 2 or 3, so bifurcation or 2 directions, such that when I remove those points, what remains is a disjoint union of open disks and annuli. So this set is called a weak triangulation. So the picture of the curve in my mind is something like this. We have skeleta. So when we remove the blue point here, we remain with annuli and perhaps some disks. So the skeleta of the annuli all together with the point of S form a graph. And this graph is called the skeleton of the triangulation S. Okay, let me show you a picture of the projective line, the affine line, and another curve. So as you may see, the interesting part, topologically speaking, of this curve, of the curves in general, is the skeleton. Because actually the curve, there is a retraction of the curve onto the skeleton. Okay, this is a non-standard terminology, so we have called this open boundary. When we have a curve, maybe at the end of this annulus, this is an open annulus, so we would like to consider a Rhobar ring here. So, naturally speaking, we are led to consider some germs of segment in the curve that are not relatively compact in it. So germs that are at the boundary of the curve, but there are no point at the end here. So you have to think to them as a germ of annuli, like in the context of the Rhobar ring. So here is the open boundary. So let me introduce, now I would like to speak about the genus of the curve and the characteristic of the curve. So there are points in the curve having a genus, okay? So let me introduce this notion now. Denote, as it is usual, k tilde, the residual field of k. Let me consider a point of type 2, so a bifurcation point. We call h of x its field and h tilde the residual field. It happens that h tilde is a field, is an algebraic extension of k tilde, whose transcendence degree is 1. And therefore, it is the field function of a unique smooth projective curve over k tilde. This curve may have a genus, so we say that the genus of the point is actually the genus of this curve over k tilde. It is an algebraic curve. Okay. If x is not a point of type 2, well, the genus is by definition equal to 0. Because in fact, in this case, we can show that x has a neighborhood isomorphic to a domain of the affine line. But if the genus is positive, there are no neighborhoods of x isomorphic to the affine line. The reason is that such an isomorphism will imply an isomorphism between the residual curve, but it is impossible because the residual curve has a positive genus. So the points, the set of points of positive genus form a locally finite set in the curve. There are not too many of them. So when you have the above description, we have an injective map from the directions out of x to the k-rational point of the residual curve. So the directions out of the point are not placed in an arbitrary way, so they follow the residual curve in some sense. They are described by the residual curve. Okay, we are ready to say what is the genus of the whole curve x. So it is the sum of two quantities. The first one here is of algebraic nature, the topological nature. So you consider the curve x itself as a topological space. So you can consider the singular homology of this topological space. Okay, so remember that the curve retracts on the graph. So it is essentially a number that takes in account the number of loops of this graph. The second quantity here is just the sum of the geni of all the points of the curve. The genus is finite. So if the genus of the curve is finite, then you must have a finite number of points with genus, with positive genus. Okay, the characteristic of the curve is then 2 minus 2g, where g is the genus, minus n, and n is the number of German segments at the open boundary of x. So the open boundary is the set of Rham rings at the boundary of the curve here. Okay. So for instance, this definition is consistent with classical one, because if x is the analytification of a smooth algebraic curve, then the genus just defined is nothing but the algebraic genus of the curve. Let me now then beginning my talk about differential equations. So what is a differential equation? So we consider a quasi-smooth curve. So a differential equation is nothing but a locally free OX model together with a connection. That is a map together with the Leibniz property. So as I have mentioned, contrary to the complex case, a differential equation of this type is not always trivial over a disk. Therefore, let me introduce the notion of radii of convergence of this equation. So we fix a triangulation once for all in this talk. So gamma S is the skeleton. So now consider a rational point. This rational point doesn't belong to the skeleton. It is inside one of those disks. So I call this disk a maximal disk. It is the largest disk containing the point and not intersecting gamma S, the skeleton. Okay, so this disk is the largest open disk with this property. Okay, and inside this disk, I may have solution, Taylor solution around X. So I have a first disk inside dxs, which is the largest disk where all my solutions converge. But some solution may converge more than this. So I may have a second disk where some solution converge. So more precisely, I have, if R denotes the rank of F, I have R disks with the property that on the ith disk, F has at least R minus I plus 1 linearly independent solutions. They are one included into the other in this way. They may be all equal each other. Okay, so once you have those disks, so the radii of convergence are essentially the radii of those disks. But the radius of a disk is not an invariant, so we have to manage to make it invariant. So the invariant notion is actually the relative disk. So if R denotes the radius of the maximal disk dxs, and Ri the radius of this disk, then we define the radius of convergence at X, the ith radius of convergence, as the quotient, Ri divided by R. By definition, it is a number less than 1. All right. So, what happens if X is not a point, is not a rational point? We can extend this definition to all the curve, actually. I do not give details about this, but I only say that our point X, every point of the curve, becomes actually rational over a larger field omega. Often omega is transcendental over K. And then we define the radii after base change to X omega. Indeed, the definition that we have just given is stable by scalar extension. Okay, so now with this set of radii, I'd like to construct a polygon. So let me say what is a polygon for me. A polygon is just a set, an increasing set of numbers. So those numbers are the slopes of the polygon. So I give to myself exactly R slopes, and then with those slopes I can construct a unique convex function that begins in 0 and that is affine of slope Si over this interval. Okay, once we have such a polygon, we can define partial heights as follow. Actually, the most important one will be the height of the polygon, okay, which is the sum of all the slopes. So let me define now the convergence polygon. I put together my radii and I define a polygon. So the ith slope is the logarithm of my radius of convergence. So we have an increasing sequence of numbers, And with these numbers, I can construct the polygon that is there. Since the radii are less than 1 by definition, I found a polygon with this shape. The most important quantity of this polygon is the height, that I call HSR. It is the product of all the radii. This quantity will control somehow the index. So, let me speak now about the continuity and the finiteness result about the radii. So I begin by telling you the story of the first radius. And the story is quite interesting. So for each point of the curve, I can associate to each point a radius. The first radius is the radius where all the solutions converge. So the first result in this direction was a result by Christol and Mep in work in '94. They have proved that this function is continuous along a skeleton of an annulus. In 2007, we have another result of continuity of Baldassari and Divizio that prove a global result of continuity over an finite domain of the affine line, plus some semi-continuity result in more than one variable. In 2010, we also have a global result, a general result that proves the continuity of this radius over any Berkovich curve, any quasi-smooth. So in this talk, when I say curve, I mean quasi-smooth. Let me now consider higher indexes. So let me do a step back for a second. So the proof of these three results is inspired by the first proof of Christol and work, and it is based on the knowledge of the resultant. I don't know the name in English. It's a basis of solution. So you control simultaneously the behavior of all the solutions. And it is difficult to isolate the behavior of an individual solution in this way. So actually, for I greater than 1, if you want to study now this function does satisfy good properties as for I equal to 1. So the first result in this direction have been obtained by Kedlaya. So he has another strategy, and he is able to prove the continuity along a skeleton of an annulus for all I. And after this, we have proved the continuity following the strategy of Kedlaya, essentially, using the strategy of Kedlaya, but we had to globalize it in order to make it work over any curve. The theorem is that this function is continuous, and more than this, it factorized through a locally finite graph that we call gamma Si of f. This graph has another property. The function along this graph is piecewise affine with locally finite number of breaks. This means that there are a finite number of numbers that control the radius, the behavior of this function. Okay? In the next slide, I will give you an image of this. So the graph is called the controlling graph of S. Kedlaya reproved the same result in 2013, but he goes further because he proved that the graph has no points of type 4. And for this, he used Tanakian methods. Okay, so if the red one is the skeleton of the curve, we have somehow a locally finite number of disks with inside some further graph, some further finite graph, where the function factorizes. So we have this retraction of the wall curve into the gamma s, into this graph, and the function is actually defined over the graph. Radii are defined over the graph and extended in a constant way outside the graph, in a locally constant way outside the graph. So for instance, the value of the function in a disk here is constant, and the value is equal to the value that you have at the branching point here. So it is enough to know the function on the graph. And we know also that in the graph there are a finite number of breaks. So it is the behavior is highly finite. So what do we do with those graphs? They are useful in giving some classification result of differential equation, usually called decomposition by the radii. So historically speaking, the first result in this direction. So let me first mention what, informally speaking, what I mean by this. A decomposition by the radii means that if you have two different solutions of your equation, then the differential equation itself split in two differential equations controlling the two different radii. So what solution are the two solutions that you had with different radii. So the first result in this direction have been obtained by Rham over the field of a point, 75. Soon after, Rham, together with Dwork, generalized this to the local ring of the curve. And their result was over the affine line. In 2000, we have another kind of result, so over the Rham ring. And in 2010, we also have a new kind of result with, which is more or less of global nature over disks and annuli. What we did in 2013 is to obtain a global kind of result working over any curve. So let me give you the theorem. So assume that for a given index I, the I minus 1 radius is strictly less than the I radius. This means that the polygon has a break in correspondence to the index I, okay? And we ask that the break remains a break over any points of the curve. So we have actually functions over the curve. And we have a polygon that moves on the curve, and we want that the break remains a break over any point. In this situation, we have a decomposition. So we have an exact sequence like this, where this differential equation has rank I minus 1, and the radii of this are the radii of f that are larger than I, while the radii of this equation are the radii of f that are strictly less than I. Okay, we are able to split our equation according to the radii. And the condition is that the radii have to be separated in some sense. So we may interpret this result over C of t. So a large class of literature is... No, well, the next slide will be... Yeah, sorry, it's not a direct sum. Not all the time. So the next time I will be... So in the next slide I will be more precise on this. So let me say just now that a large part of the literature is devoted to study differential equations over a field of power series in characteristic 0. Actually, if we consider a trivial absolute value on C, then C becomes a completely ultrametrically valued field. And the C of X can be interpreted as the ring of function over an annulus. And then this is nothing but an annulus, and actually we can show that this decomposition is nothing but the classical decomposition by the formal slopes used in literature since the work of Lagrange, I think. So usually, well, since then, all the decomposition by the radii was in direct sum. But we have explicit examples where this fails, so the exact sequence doesn't split. So we now provide a result that guarantee the sequence to be splitting, so to have a direct sum. So the first, this happens in two cases that are relatively different. The first, if the index I separates the radii also for the dual differential equation, then the sequence split. But the second criteria is more nice because it's completely topological. If we have such an inclusion of graph, so the first ith minus 1 graphs are included into the ith one, then the sequence split. So, the graphs are then important to describe algebraic property of differential equations. And a natural question is, can I measure the size of those graphs? Yes, we did it. And so that's the next topic. So but the formula, so we have found some bounds on the number of edge and vertices of the controlling graphs. But the bounds are quite disgusting, so I avoid to explain, to give details about this. So let me only say that the bound is given in terms of slopes of the radii at the open boundary of X and at the real boundary. Okay. And for this reason, if you have a projective curve, there is no boundary. So we found a bound that only depends on the rank of the equation. That means that all the equations with same rank have to have a controlling graph which is bounded by the same number, independently on the equation. So we also proved that this bound is related to the index of the equation, so to the cohomology of the equation. The problem is that the cohomology is not always finite. So when the cohomology is finite, so under appropriate condition about the exponents, then the bound is related to the index, when the index exists. So let me now speak about the index and the finiteness of the Rham cohomology groups. So first of all, I have to define an invariant that is the global irregularity of my equation. It is an invariant that controls the index. So I call with this symbol, partial zero, the open boundary of X, so the rubber rings that are at the boundary of the curve. And by B I denote a germ of segment in X, and by partial B of H, the slope of the total height of the convergent Newton polygon along this segment of the curve. Okay, so let me for a moment consider that the case where the curve has no boundary, but only possibly open boundary. In this case, the irregularity is the sum on the open boundary, on the rubber ring at the open boundary, of the slope of f along of the total height of the polygon. So you see the total height control the irregularity. But if I have some boundary, then there is another part in this definition involving the boundary. So it is the sum over the boundary of the dc of the partial height. It is again constructed with the slopes of the total height of the polygon, but given a point x in the boundary, this is the sum of all the slopes of the total height on all possible directions out of x. It is an infinite sum, ddc, but actually for but a finite number of directions, the slope is 0 because of the finiteness result that we had. So what is this key is a sort of characteristic related to a certain residual curve at a point x in the boundary. So the index theorem that I present here is somehow a simplified version of the general one. So let me assume that the curve has a finite genus. This means a finite number of loops and a finite number of points with genus. So we assume also that we have a finite number of points at the boundary, and we assume the finiteness of the skeleton. The first assumption is quite technical, and I do not give detail about this. It's an assumption about the exponents of f. So let me switch it. The radii, so the measure assumptions here is the fact that the radii of f have to be affine functions at the open boundary. So over those rubber ring at the open boundary, we want to have affine functions. So finite slopes. And also the radii, we ask that the radii are not maximal at the boundary of x. Okay, in these conditions, the dimension is finite, the dimension of the Rham cohomology, and we have an index formula. This kind of formula is also usually called the Grothendieck-Ogsa-Farevich formula. It is an index formula because on the left we have an algebraic notion, so the alternating sum of the cohomology groups, the dimensions of the cohomology groups. And on the right hand we have a sort of more topological quantities. So here we have the characteristic of the curve. Remember that this depends on the genus and on the number of segments at the boundary of the curve, the rank of f, and the global irregularity. So this is controlled by the radii of convergence. Okay, as a last remark, let me say that the assumption too about the fact that the radii are affine functions is somehow the measure assumption of this theorem. And let me say that it is automatically satisfied in some context. For instance, if you have a meromorphic singularity, and also, which is important to me, the case where the curve x embed into a larger curve in a relatively compact way, and the equation f is the restriction of another equation over y. In this case, the radii are automatically affine at the boundary of x, at the open boundary. In particular, this shows that the overconvergent cohomology is finite because overconvergence, if you have an overconvergent context, you always can restrict your boundary, your open boundary, so you can consider a smaller curve which is relatively compact into the largest one. So the overconvergent case is a particular case of the relatively compact case. Well, let me also say that we can generalize this result to all quasi-smooth curves. So under assumptions 1 and 3, so the exponents and the non-maximality of the radii at the closed boundary, we provide a necessary and sufficient condition for the finite dimensionality of the Rham cohomology. And let me say that we also investigate the case where we have meromorphic singularities. And well, this finishes my talk. Thank you for your attention.
Do we have any question for the speaker?
One small remark, maybe, just historical overview.
Sorry.
At the beginning?
No, it's okay. Just as you rightly point out, the theory of starts with work in 1960, but just a small remark that already in 1937 there was a mention of p-adic differential equations by Elisabeth Lutz, who uses them to construct p-adic elliptic functions. So it goes back a good while already, 80 years.
Thank you. Do we have any other questions or remarks? If not, we thank again the speaker.
Thank you.